We're going to be interested in locating extrema of functions. To start the discussion, I want to ask a question. How would the graph of a function look if it had a minimum or a maximum? When people are asked a question like this, they usually think of situations like this that I'll call bumps. When you've got a bump, the maximum occurs at either the high point or the low point. What's special about a bump? A bump has a tangent line that is horizontal. So the tangent line here has a derivative of 0, and the tangent line here has a derivative of 0. If you have a function that's just a constant, no matter where you draw a tangent line, the tangent line will be 0. So it seems like in these situations, a maxima or a minima has a derivative of 0. But this isn't the only way for the graph of a function to have a maximum. I jokingly say you could have pokey things, corners, that's a high point, or on a cusp you could have a graph like that. The derivative isn't 0 at the maximum anymore. The derivative doesn't exist at this maximum, or the derivative doesn't exist at this low point. You could have a graph of a function that has a removable discontinuity. According to our definition of a relative max, that point right there is the highest point in the interval, so that would be the relative maximum. You could have a situation like this. This would be the minimum. Now, in each of these situations, the graphs are not continuous. And if the graphs are not continuous, that means the derivative can't exist. If you are not continuous, you are not differentiable. It seems like at a max or a minimum, the derivative is 0 or the derivative doesn't exist. It's kind of hard to think of other situations. If I gave you the graph of a function and I said to you, okay, maybe the slope is equal to 1, could you have a maximum at the slope of 1? By definition, a maximum means that your point is higher than all of its neighbors. But if you have a slope of 1, that means as you move over a bit, the value of the graph should go up. So it kind of seems like it's not possible. I don't think so, but I'd like to be able to prove it. This is an important theorem called Fermat's theorem. And Fermat's theorem says that if your function has an extremum at x equals c, then f prime of c is equal to 0, or f prime of c doesn't exist. There are no other options possible. You can't have the derivative equal to 1. It's not possible for any of the others. But let's suppose we have a relative maximum at x equals c. And that means that the value of the function at c is greater than or equal to the value of the function at x for x near c. If I were to take f of x minus f of c, just from reorganizing this inequality, it would be less than 0. If I were to take values of x that were bigger than c, that would mean x minus c would be positive. And then if I were to divide these two, I would have a negative upstairs and a positive downstairs. So if I were on this side of c, this whole fraction would be less than or equal to 0. Now on the other side of c, so if I was less than or equal to c, that means x minus c would have to be negative. And if I were to have formed this fraction, you would have a negative upstairs and you'd have a negative downstairs. So that means that this fraction would be greater than or equal to 0. If I were to take the limit as x gets closer to c from the right, this limit would have to be less than or equal to 0. And if I were to take the limit as x approached this thing from the left, this limit would have to be equal to 0. So now there's only two options. The limits match, and the only way for these two limits to match, the only way that something that's less than or equal to 0 to match with something that's greater than or equal to 0 implies that this limit has to be 0. And that means that this limit of the above thing represents the derivative at the point c, and that would need to be 0. And the other option is that the limits don't match. And if these two one-sided limits don't match, that means f prime of c does not exist. So Fermat's theorem says if you have a maximum or a minimum, then f prime of c equals 0, or f prime of c does not exist. There's an order. This is what's called a conditional statement. You have to read it in the proper way in order for this to work. So we define what are called critical points. Critical points are points in the domain of your function where f prime equals 0 or f prime doesn't exist. So these are points on the graph of the function that either have a flat tangent line or a tangent that does not exist at that point. If you were to talk about Fermat's theorem, that doesn't hold when you go the other way. Not all critical points are minima or maxima. So you have to be careful. As an example, if I were to give you the function x cubed, its derivative is 3x squared. The derivative equals 0 when x is 0. But if I were to take a look at the graph of x cubed, there is no minimum or maximum at x equals 0. X equals 0 is neither a high point nor a low point of this function. So just because I have the derivative being 0 doesn't mean that this function has a minimum or maximum. That's not what Fermat's theorem says. I could talk about the cube root of x. Its derivative is 1/3 x to the minus 2/3, which you could write as 1 over the cube root of x squared. F prime doesn't exist at x equals 0. But if I were to take a look at the graph of the cube root, right there, it has a vertical tangent, but it's not a minimum or a maximum. So you have to be really careful. Critical points are necessary, but not sufficient for extrema. That means you have to have a derivative being 0 or undefined to have a shot at having a minimum or a maximum. But just because you have a derivative being 0 or undefined doesn't guarantee that you have a minimum or a maximum. So unfortunately, this is opposite. We are still not closer to locating minima or maxima. But Fermat's theorem is important, and in the next video we'll talk about how it comes to play to giving a method to finding minima or maxima.